Hi, it's Saltash Maths Tutor, and today I am going to be talking about logarithms. And the key thing here is that actually logarithms are really easy, promise. And it's just the way that mathematicians write stuff, just so it's all a bit confusing, that's all it is. And we're just going to go through it, and hopefully I'm going to show you an easy way to understand it. Because probably you are wondering why you have to do logarithms. Oh, it's so complicated and it's all those funny letters and numbers and goodness knows what else. Well, here's the reason why. And it's this chap called John Napier. And it's sort of his fault, but I guess really it's these other fellas here as well. It's these clever people who began to do science. And as science got more complicated, things got more complicated, and John Napier stepped in to help them. So this is what he did. And what he did was he knew that early on in science we've been doing things like 1 times 2, i.e. I've got 1 sheep, you've got 2 sheep, I wonder how many sheep we've got. Or if I double your sheep, and it was all a bit like that. It was all sheep and I've got trees and you've got 1,000 men, stuff like this. But as science progressed, as things became more complicated, we started to have greater accuracy. So this was the problem we had. So 1 times 2, you and I know that 1 times 2 is 2, easy. Well, don't want to do that. 1 times 2 is 2, nice and easy. But how about 1.1 times 2.1? These were the accuracies that were beginning to come in. That takes a little bit longer, doesn't it? But if you work it out, it's 2.31. Okay, let's get even crazier. 1.13 times 2.12. And that equals 2.3956. Now, hey, everybody in YouTube land, I'm good. I'm semi-Jedi. But I'm using a calculator here to work these things out. It had become complicated. And John Napier realised this. He realised that the more accurate we became, if we were having to multiply things, then it became really hard, quite complicated indeed. But he realised that if you had to add stuff, it was quite easy. Because look, here we got 1.13, 2.12, 3 and 2 is 5, 1 and 1 is 2, decimal term 1 is 3. Well, that took seconds. Can you imagine how long it takes to multiply that baby out? But accuracies were getting far greater, and we could have ended up with something like this. I'm not even going to spiel it out, but that sort of calculation would take a long time to do. But if we get rid of the plus, the multiply and make it into a plus, well look, term 1, 3, 4 and 5, 9, 3 and 2, 5, 1 and 1, 2, decimal 3. I've done it in 2 or 3 seconds. And so this was the idea that John Napier had. And the idea was, could he take something that was multiplication, and we've just seen how hard that was, and could he make it just simple addition? This was going to be John Napier's gift to science and maths. And we don't really need to know the massive detail of it, but he came up with some crazy idea about horse and carriages and on a road, and if one goes at one speed in a certain direction and the other one goes at a different speed, but that speed is sort of by time, you got different speeds at different things, and it all became a little bit bonkers, but you don't need to know about that. All you need to know is John Napier came up with a way of doing it. He managed to do it, and he called this crazy race the ratio of numbers. And ratio, in some ancient language, which it could be Greek, it could be Latin, this is maths, not classical studies everybody, was a logo. And in the equally classical and correct language, the word for numbers is arithmos, I think, roughly. That sort of doesn't matter. But hey, can you see it? Can you see it, everybody? This is where logarithms came from. So logarithms was just some way of converting multiplication, difficult multiplication like we did a couple of slides ago, to something easy, which was addition, which was a lot easier. He went so far even to create log tables. You didn't even need to work this out. You just had to put the numbers in and something would come out and then you could add it together. So let's just say we can't do the really hard maths of 2 times 3. I'm just giving this as an example so you can see where we're going on this one. So what he did was he created this table and you'd look up your number, 2, there it is looked up, and you'd get the log number in there. So we've got that, and then you'd have 3 and that would be its log there. So now you didn't want to do this, hard thing here, 2 times 3, so we'd have 0.3 plus 0.4 because we were really good at adding stuff up together, which would be 0.7. So you do the simple adding up thing, and then further on in the table you'd have the 0.7 and that would convert straight back to 6, which is what we've got here, and that was it. So just to sort of see that, this is what was going on. Hard thing, multiplication, big horrible nasty long numbers, didn't want to do it. Bear in mind this is our simple explanation. You could look up these hard nasty numbers, get some nice easy logs. Well, it didn't really matter. It didn't really matter because all you were doing was adding them up. Once you got your answer, you went back into your log tables, and there were books of these things. And then you'd do the inverse, if you like. You convert it back to your number. So all that multiplication thing had gone. And here you go. Here's a picture. Here's a picture of there's the log table. You see how big the book is, and here are the numbers at the bottom. And then you would look in here and get the log and do what I just talked about. But that's more complicated. And in fact, you do this all on your calculator now. But hey, we can do it ourselves. And also, poor old John Napier. Da da da. He had found the answer to this, but there was a bit of a hidden secret in here. With his method, with 2 coaches and all that sort of jazz going on, it was a bit like making a cup of tea. When I make a cup of tea, for all of you Americans who are watching, it's the same as making coffee, but it's far better tasting. I go into the kitchen, boil the kettle, tea bag, water, milk, tea bag out, tea made. John Napier's way of making a cup of tea, as a metaphor for what was going on, is he would have got on the train, gone to the harbour, got on a ship, sailed to India, gone and grown the bush, cut the tea, sailed back, dried the tea. You see what I mean? It was long-winded. It was the basis of, it was correct in what he was doing, it was just a little bit too long-winded. And in the 1700s, they discovered something. Have a go at that. What do you reckon? 2 to the power of x equals 8. What is x? Yep, you're absolutely right. X must equal 3. Because 2 cubed equals 8. That seems blatantly obvious, doesn't it? But this was going to link in with Napier's good old logarithms. So here's another one. What's half to the power of y equals 4? So from all this we get x equals 3 and y equals minus 2. And we need to think about what we're actually saying here. What we're sort of saying is 3 is the power I raise 2 by to get 8. Minus 2 is the power I raise half by to get 4. But you're probably already getting, this is quite long-winded, isn't it? 3 is the power, you feeling the pain here? Yeah, I raise 5 by to get 125. Crikey, what a... Maths would take 1 trillion years if we had to do this. 2 is the power I raise 11 by to get 100. Oh, crikey. What a nightmare. Where is the Saltash maths tutor going with all of this? Well, this is what happened. People started to abbreviate stuff. The abbreviations started to come. So instead of 3 is the power I raise 5 by to get 125, it was 3 equals the power I raise 5 by to get 125. It was just a shorter way of writing it. 2 equals the power I raise 11 by to get 121. I mean, I'll just shove that in a bracket. In fact, but that bracket makes it even neater. And you can start to play games with this sort of. We could call this the power game. There isn't any. Well, there is a power game, I guess, if we're being politicians and things. But I'm just making up the whole power game thing. I wonder if any of you are recognising anything yet, though. Because like all good mathematicians, we can start to ask other questions like, what power do I raise 5 to get 125? Or that equals 3. And you may think, hang on, he's just written this the other way around. And sort of, I have. Because I could have stuff like, what power of 3 do I need to get 27? 3 times 3 is 9, 3 9s are 27, so that's 3. What power of the number 10 do I have to raise it to get 100? Well, that equals 2. And then somebody noticed something pretty crazy. All of these things here, what power do I have to raise 10 to get 100? What power do I have to raise 3 to get 27? And what power do I have to raise 2 to get 8? Somebody had noticed something. If we cross out the word power and we put log and we calculate it, it was exactly the same as just by saying power. Cross out the word power, write log. Cross out the word power, write log. It was exactly the same. It all equaled, well, 3. It equaled the same, 3 identically, and equaled the same 2. Why didn't we change it to power then? Why didn't we have this idea of notion? Well, unfortunately, ladies and gentlemen, it was all too late. We've been using it for so many centuries and so many books, and even our calculator, actually our calculator's not quite yet, but the whole logarithm thing just stuck. But all it is just this ability to say, what power do I raise this number here to get this number, and then you get the answer. So my dear friends, in the textbook you will get something along the lines of, what is log to the base 4 64, because that's what we've now called this number. It's called a base. But with our Jedi skills, we know that we're just saying, what power must I raise 4 to get the answer 64? And I'm hoping you're going 4 4s are 16. 4 16 2 6 it's 3. Now I'd just like to point out to you here that if you bang that into your calculator, that's what you've got. But just by changing one word, this word here, and understanding what this sentence means, what power do I raise this number here to get this number here? Sometimes it can become really, really, really easy. Now, I was amazed at this, because if somebody had said to me, what's log to the base 4 64, I would have gone, I don't know. I haven't got a clue. I want a cup of tea. I want to go home. Or reach for my calculator. But that's all it is, everybody. The light bulb had come on. Logs were not a dangerous, nasty thing anymore. Actually, they're quite easy. Shall I tell you what? And here's the other thing. I can do stuff now in my head like, what's log to the base 749? Well, look, I'll tell you what. I'm just going to convert it into human. I'm just going to say, what power must I raise 7 to get the answer 49? 7 7s are 49, so it must be 7. And that's it. So that equals 7. I also know that log base 7 to get 53, if I write it as what power must I raise 7 to get 53, there isn't an easy answer because 53 is not divisible by 7. So in this case, I break out the calculator because that's what it's there for. So let's do a bit of calculating stuff, because you've actually got 3 buttons here. You've got 1, 2, 3 log buttons on there. And so let's just do this one first. All log means is that there's already a base in there, which is base 10. But again, let's put that into English. What we're saying is not log to the base 10, but what we're saying is what power must I raise 10 to get some answer. So if I've got log to the base 10 of 1,000, which for us is what power do I raise 10 to get 1,000, the answer is 3. If you can't remember that, use that log button there. It just hasn't got the little 10 on it, that's all it is. The other button is this button here, which is, you know, when we've done that, what is log 2 of 8, which if we turn into English now is what power do I raise 2 by, that makes to get 8, and we would get the answer 3, and that would be the 3 there. Well, this is the number you put in. When you put it in, it will come up as log, and you've got a flashing bit there. You type in 2, and then you'll either have to use your arrows here just to go across, and you put the 8 in there, and it's the way you change the base. If we want to talk in that old style, it's in the base, and that's what that button does there. And finally, we're going to talk about this button here. Oh, that's rubbish, isn't it? Let's put it in a bit of yellow. We're going to talk about this button here, and you're going to love this when you see it. This is the natural log, but I suppose I should call it natural logarithm, but natural log. Guess what? If I convert natural log via the power of classical Latin of Greek, again I'm neither of those things, it comes out as logarithm of this, whatever it is, naturali, I think that's what it is. So that's why it's ln, logarithm natural. It's just a natural log, and all the natural log is the log to base e. It's the power of e. Alright, and let's just say e is a number. It is a constant 2.71828, and it goes on and on and on. It's a little bit like pi. You'll come across that in other things, but it's the log base e. It's what power must I raise e to get some sort of number. So instead of writing all of that sort of rubbish, we just write log, and that's what that number is there. That's your base e thing. And so, my friends, we come to the end of this bit. There's a bit of an introduction to what a log is, because, oh, hey, unless you know what it is, how can you know what you're dealing with? Hopefully I've demystified some of the stuff, shown you some of the very basic rules, taken a canter around the calculator. In the next video I'm going to show you some of the rules of logs, and we'll do some workouts and stuff like that. I hope you've enjoyed this. This is Saltash Maths Tutor. Thank you very much.